Hi class, this is lesson 10.5. Find probabilities of independent and dependent events. Our big question here is if you draw 2 cards from a standard deck of 52 cards, is the probability that the second card is red affected by the color of the first card? So let's look at our frame. So our 10.5 frame, independent events, is about events where the first one has no effect on the second event. So that's what an independent event is. It's on its own. The first has no effect on the second. So our main idea here is if A and B are independent events, the probability that both A and B occur, which we write at the probability of A and B, it's the probability of A times the probability of B. So the probability of n independent events occurring is the product of their individual probabilities. The way I like to remember this is if you have multiple things occurring, you have to multiply. So here's our first example. It says every morning, one student in a class of 24 students, so there's our total, is randomly chosen to take attendance. What is the probability that the same students will be chosen 3 days in a row? Okay, so we have 3 different things happening. We're going to have drawings or people chosen 3 times. And every time there's 24 possible students that can be chosen. So I have 3 different things happening. So I'm going to multiply all 3 of these. There's 24 total for each one, and we want the same student to be chosen every time. So we've got 1 every time, 1 specific one that we want chosen. And if you multiply that together, you get 1 out of 13,824. The next part, if A and B are independent, the probability of A is 3/10 and the probability of B is 6/10. Find the probability of A and B. So knowing that they're independent, we know we just multiply our probabilities. So we're going to say 3/10 times 6/10, and that's 18/100. So our probability is 18/100. A spinning wheel. A spinner is divided into 10 equal regions numbered 1 through 10. What's the probability 3 consecutive spins result in perfect squares? So let's first think perfect squares. We could have 1, 4, or 9. Those are our 3 options. We've got 3 different things occurring, and we're going to multiply all 3 of those together. Each time we have 10 different options that could happen. But every time we want only 3 of them to occur. So we've got 3 out of 10 the first time that we want, 3 out of 10 the second, and 3 out of 10 the third. And if we multiply those, that equals 27 out of 100. Our next example, use a complement to find the probability. So the complement is when the probability that something's not going to happen. Okay, so if we have the probability of a coffee pot being defective, its complement would be the probability that it's not defective. So this says a manufacturer has found that 2 out of every 500 coffee pots produced are defective. What's the probability that at least 1 coffee pot is defective in the first 300 coffee pots made? So first of all, we want the probability that a coffee pot is defective. And so we know we've got 2. Let me get my pen. We've got 2 out of 500. That's a probability that it's defective. So that'd be 1 out of 250 are defective. So then the complement to that, the probability that a coffee pot is not defective, well, that's going to be 498 out of 500, or that equals 249 out of 250. So those two are complements. One or the other must occur. It either is defective or not defective. So part B here, each coffee pot made is an independent event. So the probability of making at least one defective pot is the probability of at least one coffee pot and 300 being defective. So we can do 1 minus the probability that none of the coffee pots are defective. So to find this, the probability that at least one coffee pot is defective, we're going to do 1 minus, and now our probability that none of the 300 coffee pots are defective, well, our probability for one not being defective is 249 out of 250. But we have that 300 times, so we need to raise that to the 300 power. So it's 1 minus, that's a minus sign there, 249 out of 250 to the 300th power. That's about equal to 7/10. Okay, let's flip your frame over. Now we're going to talk about dependent events. Okay, so this side is dependent events. So these are events where the first one does affect the second event. So independent, they're on their own, they're separate. Now we're going to talk about where the first one does affect the second event. So our main idea here, the probability that B will occur given that A has occurred is called the conditional probability. And I'm going to try and write this. I don't have my pen right now, so it's kind of hard to write small. Conditional. This should go in this little blank. Blank should have been bigger. It's called the conditional probability of B given A. And we write it like this. It looks like this. This is the probability of B, that bar we read, given A. So if A and B are dependent events, the probability that both A and B occur, so that's the probability of A and B, is the probability of A times the probability of B given A. So now we're going to find a conditional probability. So events A and B are dependent. Okay, so for our first one here, the probability of A is 3/10. The probability of B given A is 6/10. And we know, again, we're just going to multiply those because we have multiple things happening. So we're going to do 3/10 times 6/10. And that equals 1800ths. A down here says find the probability of a listed person has blue eyes. So if you added these all up, you'd have 200. There's 100 in male and 100 in female. So our blue eyes, well, that's 35 plus 9. Okay, it's this right here. There's our blue eyes. So 35 plus 9, well, that's 44 out of 200. And if you reduce that, because we should always reduce our fractions, that's 11 out of 50. Next, the probability that a male has blue eyes. Okay, so now we're only talking about males having blue eyes. So a male with blue eyes is right here. That's 35. So the probability that a male has blue eyes, so the probability of blue eyes given that it's a male, that's 35 out of 100. And if you reduce that, it reduces to 7 out of 20. Next, find the probability that a female has hazel eyes. So we want the probability of hazel eyes given that we've got a female here. So hazel eyes for a female is right here, and that's 41 out of 200. And if you reduce that, well, you can't. I'm sorry, not 41 out of 200, 41 out of 100. So 41 out of 100, that can't be reduced. Next says your teacher passes around a box with 10 red pencils, 8 pink pencils, and 13 green pencils. If you and the 2 people in your group are the first to randomly select a pencil, what's the probability that all 3 of you selected pink pencils? So we've got 3 things happening, so I'm going to write a fraction bar for all 3 of my things, and we're going to multiply them together. And if you add it up, we have 31 total pencils to choose from. So the first person who chooses, they have 31 pencils to choose from. And we want them to have a pink. So there's 8 out of 31 chance that they'll choose a pencil. Now the next person, they've got to choose a pencil, but there's one less pencil there. So now there's only 30 pencils, and 7 of them are pink. And then the third person, well, now there's only 29 pencils, and 6 of them are pink. So if you multiply that all together, you get 336 out of 26,970, and that actually will reduce to 56 out of 4,495. So this one was a little bit different. Notice, remember, our bottom we had to reduce because you're not going to put the pencil back. The next person has one less pencil to choose from. Okay, and let's look at the final part of our frame for 10.5. This is about comparing dependent and independent events, is about knowing when events are independent and when they are dependent. Okay, so when they're on their own and when the second thing depends on the first. So example 1, you randomly select 2 marbles from a bag, containing 15 yellow, 10 red, and 12 blue marbles. So right now I'm going to think, okay, what's my total number of marbles right there? Well, I've got 37, so there's my total marbles. What's the probability that the first marble is yellow and the second marble is not yellow if, first of all, we're going to replace the first marble before selecting the second. So if we replace it, then these are 2 independent events, because what happened the first drawing doesn't affect the second one. So first of all, we want a yellow marble. So the chances of getting a yellow marble are 15 out of our total 37. We have another thing happening, so I'm going to multiply by. And I'm replacing it, so I still have 37 marbles left in my bag. And the marbles that aren't yellow, well, there's 22 of them. So 15 out of 37 times 22 out of 37, and that's 330. 330 out of 1,369. So now this changes a little bit. If you do not replace the first marble, still we first of all have 15 out of 37. That's our probability the first time of getting something that is yellow. But next we only have 36 marbles left in the bag because we're not putting that first one back, but there's still 22 that aren't yellow left in the bag. So if you multiply those, you get 330 out of 1,332. So we just multiply straight across, remember, and that equals 55 out of 222. Example 2 here, it says find the probability of drawing the given cards from a standard deck of 52 cards. So first we want a spade and then a club with replacement. So with replacement, these are 2 independent events because both times, if I'm putting it back, both times I have 52 cards. First I want a spade and there's 13 spades. Put it back, so I still have 52 cards, and then I want a club, so there's 13 clubs. And if you multiply that and reduce it, you get 1 out of 16. So the next part here is if we do it without replacement. So I still have a chance, 13 out of 52 of getting a spade, but if I'm not replacing it, I only have 51 cards left in my deck. So my probability of getting a club then is 13 out of 51. And if you multiply that and then reduce it, you get 13 out of 204. So our next one here, if we want a spade, then a club, then another spade, first of all with replacement. So I've got 3 things happening. I need 3 fractions and they need to be multiplied. If I'm replacing my cards, I have 52 cards in my deck every single time. So first time I want a spade, there's 13 spades. Then I want a club, there's 13 clubs. And there's still then going to be 13 spades left because I'm putting my card back. And if you multiply that together, you get, and then reduce it, you get 1 out of 64. If I then do this without replacement, I still have 3 different things happening, so I need 3 fractions. My first time I'm going to have 52 cards, then I'm going to have 51, and then the third draw I'm only going to have 50 cards left. So if I first want a spade, I have 13 spades. If I want a club, then I have 13 clubs. And then if I want a spade again, now I only have 12 spades because I drew one the first time. Multiplying, reducing, you get 13 out of 850. Okay, and then we already did this one. I'm not sure why it's back. The so what here, the thing that I want you to remember, what's really important for these problems is when you have multiple events, so more than one event, multiply. We're not adding for these, we're multiplying. When we have multiple events, we multiply. And that's the end of lesson 10.5. Make sure if you have any questions, you star them so we can talk about them in class tomorrow. Have a great night.